All right, everybody. Today I'm going to be teaching you guys a little bit about melting point determination in an organic chemistry lab. So, a couple of basic principles about melting points. So the melting point of a solid is determined by the intermolecular forces in the sample. And so things with stronger intermolecular forces are typically going to have higher melting points. This is why things like hexane and diethyl ether are going to be liquid at room temperature, whereas things like large carboxylic acids or alcohols are going to be solids because they have stronger intermolecular forces. In addition to that, there are some other major factors that can influence the melting point that we measure in the lab, and most of these can be due to variability in experimental protocol. Some of these involve sample preparation, the program on the melting point apparatus, and then impurities present in the sample. Finally, one key point that I'm going to talk about, whenever we're recording a melting point, we actually record a melting range, not a melting point. So we're going to record two temperatures. The first temperature that we record is always going to be when we begin to see the sample melt. And this will make more sense when I'm actually showing you how to do this on the instrument. But basically, we're going to be looking in a magnifying glass at our sample inside this heating block, and we're going to be able to watch it melt. And so we're going to record the temperature when it starts to melt, like when we first see droplets of liquid forming. And then the second temperature we'll record is when no solid remains. All right, so to talk about sample preparation, we typically take melting points in these capillary tubes with one closed end, and then the other end is open. To prepare this sample, we tap the open end against the solid product to pack it in, and then we just tap it down into the bottom of the tube. The goal is to get about 1 to 2 millimeters in the very bottom of the capillary tube, as shown in this picture here. Now, if we have too little sample in the tube, it'll be really hard to see through the magnifying glass when we have it in the apparatus. So it'll be really hard to determine what the melting point is. And then also the melting point, even if we can see it, the melting point will probably end up being low. If we have too much sample in the tube, the melting point is going to be high. It's just going to take time to melt the sample because there's more of it. And as that sample is melting, the instrument's going to continue heating up. So you're going to record, the temperature that you're going to record is going to be an artifact of the fact that it took a lot of time for the sample to melt. And so that's why you're going to see a really broad melting point range, in addition to your melting point being high. Now, on the melting point instrument itself, there are going to be 3 settings, and I'll show these to you again when I'm actually in front of an instrument showing you how to do it. But there are going to be 3 settings. One of them is going to be the start temperature, one of them is going to be the ramp rate, and one of them is going to be the stop temperature. Now the start temp, we typically set that about 10 degrees below the literature melting point. And this is just in case our sample melts a little bit lower than we expect it to. That way we'll be able to see it and still get an accurate melting point. What we want to avoid is putting the sample in the instrument and instantly having it melt, because then we know it melts at the temperature that the instrument's set at, but it could melt significantly below, and we get no information from that. The second setting is going to be the ramp rate. This is how fast the instrument increases the temperature of the block. Typically we want to set that at about 2 degrees per minute. The reason we want to avoid setting higher than that is because if our ramp rate is too high, what can happen is that, again, the sample takes some amount of time to melt once it reaches its melting point. And so we can, with a high ramp rate, we'll also get a broad range and record a melting point that's too high, similar to what we would have happen if there's too much sample in the tube. However, if we have the ramp rate really, really high, like 10 to 20 degrees per minute, something called thermometer lag can actually occur. And what that means is that the thermometer that is measuring the temperature of the block, that we're actually reading off, is different than what the actual temperature of the block is. So the thermometer, the digital thermometer isn't accurately reading the temperature of the block because the temperature of the block is changing too rapidly. And if that happens, the melting point will actually register as too low because the block will be hotter than what the thermometer says it is. So we'll see it melt, and the block is actually at the melting point of the compound, but the thermometer is low. And so the recorded, or what we observe as the melting point, will be too low. And then the stop temp, just like the start temp, we just want to set it about 10 degrees above, so we've got a nice range so we don't miss anything. Finally, impurities will disrupt the crystal matrix in the solid, which will weaken intermolecular forces. This in turn will lower the melting point. So just to kind of draw this out for you. So if we have a graph here, on the y-axis I'm going to put temperature, and on the x-axis we're going to have how much of each compound we have. So if we have 100% compound A, and we take a melting point of it, its melting point is going to be at the melting point of compound A. If we have 100% compound B, and we take a melting point, the melting point for compound B is what we're going to observe. Now, if we start to add a little bit of B to A, what's going to happen is this temperature is actually going to dramatically decrease. So even with just a tiny amount of B present, the melting point that we observe is going to be a little bit lower than the literature melting point of A. Now at about 50-50 is where it bottoms out. So that's the lowest temperature that we're going to observe. And then as we add more B, then it's going to approach the melting point of B. But no matter what, having impurities in a sample is going to lower the melting point. So now we're just going to go ahead and look at the instrument and get right into it.
Okay, hi everybody. Today I'm going to be explaining how to take a melting point of a solid compound. So what we're going to need is our sample here, and we have a glass capillary tube that's open on one end and closed on the other. So this will allow us to collect the sample and then go ahead and melt it. So to collect a sample, I'm just going to take the open end of this capillary tube, and I'm just going to tap it repeatedly against my crystals. And this is just going to go ahead and start to pack some of this solid inside the mouth of this tube, as you can see there. Now, once I've got it inside the tube, I actually have to tap it down all the way to the bottom of the tube. And with this compound, it's actually relatively easy. So now you can see it's down there at the closed end. One thing, when you're preparing melting point samples, it's really critical to make sure that your crystals are really dry, that they don't have any water or solvent on them. Because if they have any water or solvent on them, that'll cause them to be really sticky, so it'll be really difficult to get it to pack into the melting point tube. But if they're nice and dry, they should pack relatively easily. Now, what we want is we want to get approximately 2 millimeters of sample in the bottom of the tube. So that there is probably enough of our compound to be able to get a good melting point. If you have too little, your melting point will be low, and so it'll, and if you have way too much product in there, your melting range is going to be really broad, and you're going to end up recording a higher melting point than you otherwise would have. Now, a couple other things can affect melting points. So, when you're taking a melting point of a compound, if there is impurity present, that will lower the melting point of the compound. And so oftentimes when we take melting points, we expect them to be a little bit lower than the literature value for a compound. And like I mentioned, the amount of sample that you pack in the melting point tube can also impact the temperature at which the compound melts. The third factor, which I'll talk about in a moment, is going to be the ramp rate on the instrument, or how quickly we are increasing the temperature in the melting point apparatus. So this is a melting point apparatus. So over here we have the controls, and then here we're going to be able to see inside and watch our sample melting. So basically this is just a controlled heating block that we can carefully control the temperature on. So I'm going to go ahead and set up a melting point program. Now the melting point, the literature melting point for the compound that I'm melting right now is 134 degrees. So I'm going to go ahead and set my start temp at about 10 degrees below the literature melting point. The reason we do that is because, like I mentioned, oftentimes we expect these melting points to end up being a little bit lower than literature, so we want to give ourselves enough space that if the compound does melt a little bit below its expected melting point, we can still observe it and get an accurate melting point. The second thing I'm going to do is I'm going to set a ramp rate. Now this is how many degrees it's going to heat up each minute. Now 2 degrees is typically a good setting for this. You'll notice we have the option of 5 or 10 degrees per minute. The reason that those are inappropriate is because the onboard thermometer that measures the temperature of this heating block might not actually be able to keep up with a ramp rate of 10 degrees per minute. So that's a phenomenon referred to as thermometer lag, meaning that the block will actually be hotter than the displayed temperature on the instrument. Now the reason that's an issue is because it can lead to you recording a melting point that's lower than the actual melting point of your compound, so it introduces error to the experiment. So a ramp rate of 2 is typically a good choice. And then for stop temp, we just want that to be above the literature melting point of our compound, just to make sure that if our compound melts a little high for some reason, we can see that as well. Then I'm going to go ahead and hit start over here until it goes to the preheat setting. So this is going to take a little bit of time to heat up to 125, but then it'll be ready to go. Alright, so it's been a couple minutes, but our instrument is now heated up and ready to go. You'll notice the green ready light has turned on. So what I'm going to do is I'm going to go ahead and take my sample, and I'm actually going to insert it here in one of these 3 holes in the top of the melting point apparatus. So as I insert it here, notice now if we look through the viewfinder, we can actually see our crystals here inside the melting chamber. So now that those are in there, I'm just going to go ahead and come back over here, and I'm going to hit start one more time, and that's going to go, and as you can see, the melt light is now on. That means we're ready to go, and the program is running. So I'm going to come over here. Now we're just going to watch through the viewfinder. Now, the important thing here on this to note, we're going to record a melting range, not a melting temperature. So we're going to record 2 temperature points. The first temperature that we're going to record is the very first time that we see signs of melting. So this is going to be either beads of moisture forming, which we refer to as sweating, or the crystal will start to kind of cave in on itself. Either of those are signs that the crystal is starting to melt, and so when we see either of those, we're going to go ahead and record that temperature. The second temperature we'll record is when there's no solid left, when it's just a liquid. So I'll point out those 2 temperatures as we're watching this. So here we're at 130 degrees, 131 really, and looking through the viewfinder, we're still not really seeing any major signs of melting, which means that our crystals are actually pretty high quality because the melting point of this compound is 134. So we'll just go ahead and keep watching for a little longer. We should start seeing sweating pretty soon. So now it's 132 degrees, and if we look in here, now I'm definitely starting to see signs that the crystals are starting to melt. They're becoming more translucent. They're also starting to crumble in on themselves a little bit. Nothing dramatic at this point, but I would go ahead and record 132.0 degrees as the point at which they started to melt. You can also, if you look closely, see a little bit of liquid accumulating in the bottom of the tube. So just going to go ahead and keep watching these. Now they're definitely almost completely melted. Just going We're at 133.9 degrees here, and I think all of the crystals have finished up melting. So for my melting point range on this sample, I would record 132.0 to 133.9 degrees. That would be the melting point that I would record for this sample. So once we've taken the melting point, we can just go ahead and dispose of the capillary tube in the broken glass. And we'll just go ahead and hit stop on the instrument so that it will cool down, and we finish taking our melting point.